Okay, so now that we kind of look at the properties of waves, okay, so we know kind of what things are important for a wave, we need to look at what's called the universal wave equation. The universal wave equation is super easy to use. It's just a 3-variable formula. Essentially, it's V equals D over T, but using the properties of a wave instead, right? It helps us to calculate the speed of the wave, the wavelength of the wave, okay, and the frequency of the wave, right? That's what it'll help us to do, right? So we need to look at what affects the speed of a wave, okay, and what happens essentially when a wave changes speed, what can happen to it, right? And learn to use the universal wave equation, which, like I said, is a super easy formula to use. All right. So how fast does a traveling wave move? Well, we could calculate that if we could measure how far the wave travels and time how long it takes to do that. And sometimes you can do that. But a wave isn't a solid object. Waves have indistinct boundaries and they change shape. So it's difficult to pick a point on a wave that is always going to be exactly the same shape and accurately measure where that wave really is at any given time. Okay, so yes, we could use V equals D over T, but it's sometimes easier to use other formulas or other properties of the wave to calculate its speed instead. Now, we were talking about this just a few minutes ago when we watched the tsunami video. Okay, out on the water in the deep ocean, waves are long and they're slow. Sorry, they're long and they're fast. Sorry, I said that backwards. They're long and they're fast. Okay, but as they approach the shore, the properties of the water change. That is, it gets shallower, right? Because it's getting shallower, there's more interaction with the bottom, which slows the wave down. But of course, the front of this wave is going to reach the shallow water before the back of the wave does. So the back of the wave continues to travel fast, the front of the wave tries to travel slower, and the wave gets shorter. Okay, so speed slows down, the wave gets shorter, the wave gets taller. Okay, and that's why we see them rip and curl and stuff near the shore. Everybody okay with that? Okay, it's very much like what you would see on the highway. Okay, just out here actually, where the speed limit inexplicably changes from 100 to 60. And it could, easily stay at 80, but whatever. Okay, what happens here is we've got our road. Okay, and right here is where the speed limit changes from 100 to 60. Okay, so out here I've got 3 cars. Right, and they're all traveling at 100 kilometers per hour. The first car has to slow down before the others because it reaches the change in speed limit. So as it slows down, the car behind it will catch up, and the car behind that one will catch up. Right, but if I'm standing right here, I see 3 cars go by in 1 second. Let's say it takes 1 second, and all 3 cars go by me in 1 second. Right? If I stand over here, am I still going to see 3 cars go by me in a second? I am. Why am I going to see the same number of cars go by every second if they're slowing down over there? They get closer together. Exactly. Just like in a wave, okay, the crests get closer together because the wave has slowed down. So what I see over here is now 3 cars tailgating each other because one is caught up to the other and not maintain the spacing. Right? So now they're going slower, but they're closer together. The frequency doesn't change. Okay? Just the wavelength and the speed. All right, so important thing to know here, and you're gonna need to write this down. I'm gonna tell it to you like a dozen times today, okay? But frequency never changes. Wavelength, speed, they'll change. Direction, that'll change. Amplitude, that'll change. But frequency will never change. Once a wave is produced, its frequency remains the same. Okay? If that were not true, okay, then light could change color spontaneously, okay, and sounds would be like significantly altered, things like that. Okay, once a wave is produced, its frequency remains the same always. Okay. Okay, so the speed of a wave is dependent on the properties of the medium in which it's traveling. Medium controls speed. Yeah, essentially, it's also focusing the waves a little bit, right? Having the glass, the shape of the glass will do that. But yeah, when you put the cup against the door, and you have to actually be touching the door with it, right? The vibrations of the sound that hit the door are transferred to the glass, which is a better way to transmit the sound waves to the air inside the cup. Yeah? All right. So everybody with me there? The big thing here is that the speed of a wave is dependent on the properties of the medium. Okay? Lots of things can change the speed of a wave. Right? For example, the speed of sound changes depending on what the temperature of the air is. The cooler the air, the faster, the slower the sound waves will travel. Okay? The cooler the air, the slower the waves travel. Right? Hotter air, sound travels faster. Okay? Right now in this room, the speed of sound would be about 340 meters per second. Okay? If it was at freezing, it would be about 330 meters per second. Right? So it does change, okay, with the properties of the medium. Okay? And we saw that the depth of water also changes the speed of the wave. Okay? Everybody okay with that? Okay? So the properties of the medium determine the speed of the wave. Sound waves, okay, and they travel through air, like we said, about 340 meters per second. When they hit that door, they speed up. Sound waves travel way faster through solids than they do through gases. Okay, so gases are actually one of the slowest things. Okay, so if you have a sound wave going from air to water, it'll go from 330 meters per second to about 1500 meters per second. Okay, sound travels way faster in water than it does in air. Okay, so when we're dealing with waves, okay, the characteristics of the wave we want to use would be speed, wavelength, and period, or speed, wavelength, and frequency. Most of the time, you will see the universal wave equation written like this. V equals F, frequency, times wavelength, lambda. That's the way it's written on your formula sheet. Okay, it can also be written like this because obviously F is 1 over T. Okay, so that's what this would be, lambda over T instead of lambda times F, right? We're just saying F is 1 over T. Okay, so really all we're doing with V equals D over T is determining what the distance and the time are going to be. The speed of a wave is its wavelength divided by the time it takes that wavelength to happen. Okay, so wavelength divided by period, right? That's what this essentially is. V equals D over T, because wavelength is measured in meters, period is measured in seconds. Right? So it is a really easy formula to use. It's just a 3-variable formula. Okay. Questions on that part there? Everybody's okay with that? All right, so let's say we have a sound wave that has a frequency of 262 hertz and a wavelength of 1.29 meters. What's the velocity of the sound wave? Well, V equals lambda times frequency. Okay, they told me the wavelength was 1.29 meters. They told me the frequency is 262 hertz. I measure them, I multiply them together, and I get that the speed of that sound wave is 338 meters per second. Okay, so really super easy formula to use. Now, the only thing that can get tricky about the universal wave equation is if I give you a question like this. I want you to write this one down as an example. Okay, so I've got 5 wave crests that go by me. Okay, and I note that that takes 30 seconds. It takes 30 seconds for all 5 wave crests to go by. Okay, the crests are 2 meters apart. Okay, what's the speed of the wave? All right, what are some things that this question has given me? Connor? It's given me the wavelength. Okay, any 2 equal parts of a wave, okay, the distance between those 2 equal parts is the wavelength. All right, so essentially what we're looking at is this. We have kind of this situation here. Imagine those are all the same. They kind of got bigger as I went along. Okay, so we're saying that from here to here is 2.0 meters. Well, that's the wavelength then. Okay, I could have also said it's 2 meters between 2 troughs. Okay, that's the bottom part of the wave, right? So I could have said it's 2 meters between the troughs, and it would be the same. It would be the wavelength. Okay, it's any 2 equal parts on a wave. Now, it took 30 seconds for these 5 crests to go by. What can that help me find? Period or frequency, either one. And I can use either one in the formula. But what I need to know is how many waves went by. How many waves went by? 4. Only 4 complete cycles went by. 5 crests went by. That's only 4 cycles. Okay, here's where we started. This is essentially like crest 0. So here's one wavelength right here. From here to here is one wavelength. From here to here is 2 wavelengths. From here to here, 3. And from here to the last crest, that's only 4 wavelengths. It's 5 crests, but it's only 4 cycles of the wave. Everybody kind of follow me on that? That's the only trick that can happen with the universal wave equation. So anytime they tell you it's this many crests or it's this many troughs, it's 1 less than that for the number of waves. Sometimes the question will just say it's this many waves, and that's fine. But once in a while, they'll do this because it's really the only trick. Okay? For a 3-variable formula, there has to be something out there to try and trip you up because a 3-variable formula sure as heck isn't on its own. Okay? All right, so now I know that there are only 4 waves. That took 30 seconds. So I want to calculate the frequency. I'm going to go cycles per second. So I have 4 cycles divided by 30 seconds. Okay, so my frequency is 0.13 hertz. Now that I have that, okay, so F is 0.13 hertz. I could have also found period. It doesn't matter which way you do it. Okay. Now I can use this formula, V equals F times lambda. Okay, so that'll be 0.13 times 2 meters. That was our wavelength. I actually just did that. I can't believe I actually just plugged that in. Okay, 0.26 meters per second. Everybody kind of follow on how that one would work? Okay. Other ways that a question like this can try and throw something at you that makes it seem kind of odd is it might just tell you it's a radio wave is traveling through here. What do all radio waves, what speed do they travel at? What kind of waves are radio waves? Light waves, right? They're radio waves, electromagnetic waves, anything like that. They all travel at the speed of light, okay? And the speed of light is listed on your formula sheet. Under other useful constants, it's 3.0 times 10 to the 8 meters per second, okay? So any type of light wave travels at that speed. The other thing it might do is it might say a sound wave is traveling through air and the air temperature is this many degrees Celsius. Well, we already said a few minutes ago that the properties of the medium can affect the speed of the wave. So I have to use the temperature of the air to calculate the speed of the waves. That formula is also on your formula sheet, but this is what it looks like. The speed of a wave equals, I don't know why I put T in there. Okay, speed of a wave is 332. That's the speed of sound at 0 degrees Celsius, plus 0.6 times the temperature in degrees Celsius, which is the only thing you'd ever get it in. Okay, so 332 plus 0.6 T will give you the speed of the waves. So if it tells you the air is 20 degrees Celsius, then you just plug 20 in for temperature and you'll have the speed of sound. Only for sound, yes. Okay, because like we said, light, 3.0 times 10 to the 8. All right. So we'll have a look at this one here first. So if I want to generate waves in a stretched spring, okay, we oscillate our hand back and forth at a frequency of 2 hertz. Okay, so basically we're just, and I'm going to do this probably tomorrow or the day after, we'll take our slinkies out and make waves. Okay, so you oscillate your hand back and forth with a frequency of 2 hertz. So that means you're doing it twice per second. Okay, the speed of the waves is 5.40 meters per second. What's the wavelength? All right, so they've given us F, okay, 2.0 hertz, and they've given us V, 5.40 meters per second. We are looking for lambda. Okay, so V equals F times lambda. How do I get lambda by itself? Divide by F, right? Okay, so now I've got that. So we'll go 5.4 divided by 2.0. Okay, and we're going to get 2.7 meters. Okay, as our wavelength. Again, it is a very easy formula to use. Okay. Questions on that one? Okay. For right now, try 1 and 2. We'll get to the echo question in a minute. Okay, so I have a submarine system that sends a burst of sound with a frequency of 325 hertz. The sound wave bounces off an underwater rock and then returns 8.5 seconds later. The trick to this is that it's an echo. How far does an echo travel? Twice whatever the distance is to the rock, right? It has to bounce off the rock and come back. And that's the trick with all echo questions. So anytime you have a question where it's using an echo, it's either half the time or twice the distance. Okay, you got one or the other that you've got to do. Okay, so in this case here, okay, we have the frequency. We know that. Okay, the frequency is 325 hertz. Right, and then it returns to the submarine in 8.5 seconds. So we really just want the time to the rock face. So we just need 4.25 seconds because that's how far it is to the, or how long it takes to get to the rock face. Okay. The wavelength, lambda, is 4.71 meters. Okay, how far away is the rock face? All right, so I've got lambda and F. If I want to find D, I need V and T. So I can use F and lambda to get V. So V equals F times lambda. So 325 times 4.71. Okay, so 1,530.75 meters per second. Like I said, water travels about 1,500 meters per second in water. All right, so very, very fast. Now that I have that, now I can find D. Okay, so D is going to be V times T. So we got V. They told us it takes 8.5 seconds to get there and back. So times 4.25 is how long it took to get there. Okay, so that means that it is 6,505 meters. Actually, there's only 3 significant figures there, so 6.51 times 10 to the 3 meters would be how far that rock face is away. All right, everybody okay with that one? All right, how many people didn't realize that's what they had to do? Yeah, and that's usually the case. The first time you do an echo question, you just forget that, oh yeah, an echo travels there and back. All right, so that means then, okay, have a look at number 3. So a fisherman anchors his dinghy in a lake 250 meters from shore. The dinghy rises and falls 8 times per minute, and he finds that it takes a wave 3 minutes to reach the shore. How far apart are the wave crests? Okay, so give that one a try here. We'll finish off with that one. Okay, so he's 250 meters from shore. Okay, so we know that they're going to, the waves, this is possibly a distance they're going to travel. Okay, the dinghy rises and falls 8 times per minute. Okay, so those are 8 complete cycles. This isn't like the wave one I showed you a minute ago where it said it was 8 crests. This is 8 cycles. It does in fact say it goes up and down. Okay, so that's 8 waves in 1 minute, right? Do I want it in waves per minute? Probably want it in waves per second, right? So I'm going to divide that by 60 so I get my frequency in hertz. All right, so 8 divided by 60. right? And I've got 0.13 hertz. Okay, so I've got frequency, and he finds that it takes a wave 3 minutes to reach the shore. All right, so that's 180 seconds. So my time is 180 seconds. The distance they have to travel is 250 meters, and I have the frequency. We're looking for how far apart are the wave crests. What do we call the distance between two equal points on a wave? Wavelength. So that's what we're looking for here, okay, is we're looking for lambda. So first we're going to want to find V. V equals d over t, so 250 divided by 180 will give us the wave speed. Okay, so our wave speed is 1.38 repeating meters per second. Now that we have that, now we can find lambda. Lambda is going to be V over F. Everybody all right with that? Okay, just manipulating the universal wave equation. So we'll take our number there, okay, and divide it by 0.13. All right, so these are long waves. They're 10.7 meters in length. Okay, now just back to one other thing here, guys, before we pack up. Okay, and that is the relationship here. Okay, V equals F times lambda. We said this number can never change. The frequency of a wave never changes. So if I'm solving for F, okay, these are the two properties of a wave that can change. V and lambda can both change. But if V gets bigger, what does lambda have to do? If F is never going to change, when V gets bigger, F gets bigger. They have to do exactly the same thing. Their ratio has to stay the same. If V gets 3 times bigger, lambda gets 3 times bigger. All right? They have to increase the same or decrease the same, okay, in order to make sure that frequency never changes. I think I've now said that 8 times. Okay, I said I was going to get to about a dozen, but I didn't. I will tomorrow. I'll finish it off. Okay, frequency never changes. That's 9. Okay, that's why V and F have to do the same thing, right? And we said as they approach the shore, the waves get slower and they get shorter. Right? They're doing the same thing. They got shorter, they got slower. They got taller, but amplitude's not part of that equation. Okay, so as they got shorter and slower, okay, that meant that frequency stayed the same. That's 10. Okay, so we're good. Okay, everyone's going to remember that. All right, tomorrow's Tuesday. You haven't had a quiz in about 3 weeks. You will have one tomorrow. Okay, it'll be on simple harmonic motion and energy. So, okay, I'll post it later on today. Have a quick look at that.